Our universe carries the faint scars of its entire violent history. Every colossal event, from the formation of the first galaxies to the explosive death of stars, has left a permanent imprint, like ancient writing on a parchment that has been used again and again. This is the great Cosmic Palimpsest, the central idea that the cosmos preserves its past even as new events overwrite it. By the end of this exploration, you will understand how scientists are learning to read these ghostly signatures, fundamentally changing our story of reality. We will investigate why the oldest light in the sky contains a mysterious cold spot, and how the faint ripples from black hole collisions might tell a story that predates time itself. What part of the universe's forgotten past feels most intriguing to you? That ancient manuscript, scraped clean and written over, is a perfect mirror for our cosmos. Just as ultraviolet light can reveal the ghost of older words on that reused parchment, advanced telescopes can detect the faint, residual glow of the universe's infancy. This is the cosmic microwave background, the afterglow of the Big Bang itself, and it is the most profound palimpsest we have. It is a snapshot of the universe when it was just 380,000 years old, a baby picture frozen in light. But this picture is not perfectly uniform. It is marked with tiny variations in temperature, subtle hot and cold spots that are the imprints of the universe's very first structures. These are the original words written onto the cosmic page. The great eraser, however, is the relentless expansion of space itself. This expansion stretches the wavelengths of light, dimming and distorting the signals from the past, making them incredibly faint whispers against the roar of more recent cosmic events. New writing is constantly being added too. The violent deaths of stars, the collisions of galaxies, and the frenzied feeding of black holes all imprint their own dramatic stories onto this cosmic parchment, partially obscuring the older text beneath. Yet, the original writing never completely vanishes. Scientists decode these layers by looking for specific signatures, like the polarization patterns in the ancient light. These patterns can act as a fossil record of primordial gravitational waves, ripples in spacetime from the universe's first explosive moments of inflation. It is as if we are learning to read the invisible ink of creation. So, if the universe is this vast, layered manuscript, how do we build the tools sensitive enough to read its faintest, most overwritten passages? These sensitive telescopes, scanning the microwave hum of the cosmos, are our time machines. They are not looking at stars or galaxies, but at the very fabric of space, which glows with the remnant heat of the universe's violent birth. This is the cosmic microwave background, the CMB, and it is the oldest light we can see. It is a fossil imprint from when the universe cooled enough for atoms to form and light could finally travel freely, a moment frozen just 380,000 years after the Big Bang. The map of this light is not a featureless glow. It is an intricate tapestry of incredibly subtle temperature differences, tiny variations of mere millionths of a degree. These hot and cold spots are not random. They are the Cosmic Palimpsest's foundational text, the imprints of quantum fluctuations that were stretched to cosmic size during a period of hyper-expansion called inflation. These minute density variations are the seeds for everything we see today. The gravitational wells that would eventually pull in matter to form the first stars, galaxies, and clusters. So how do these tiny temperature differences tell such a grand story? Each fluctuation is a direct record of the density of matter in that region of the young universe. The cold spots are slightly denser patches where gravity had a stronger grip, and the hot spots are slightly more rarefied voids. This baby picture contains the blueprint for the entire cosmic web. But the temperature map is only the first layer of writing. The light of the CMB also carries a specific orientation, a property called polarization. As this ancient light scattered off the first particles, It was imprinted with patterns. One particular pattern, known as B-mode polarization, is the holy grail for cosmologists. It is the predicted signature of primordial gravitational waves, ripples in spacetime itself generated during the universe's inflationary first moments. Detecting this signal would be like reading the very first sentence written on the cosmic parchment, a direct glimpse into a time before the CMB was even created. This incredibly subtle search is the work of missions like the Planck satellite, which has mapped the entire sky with breathtaking precision. Planck's data has refined our understanding of the universe's age and composition, but it has also revealed something deeply puzzling: large-scale anomalies. There are features in the CMB that should not be there according to our standard models. Vast cold spots and alignments that hint at physics we do not yet understand. Some speculate these could be scars from a collision with another universe in the multiverse. Distilling a clear signal from the noise of intervening space is a monumental task, requiring sophisticated statistical analysis to separate the primordial whisper from the roar of galactic dust and other foregrounds. This first method, reading the universe's oldest light, gives us our deepest look back. But what if we could read a different kind of history, one written not in light, but in the silent, ghostly ripples of gravity itself? Gravity writes its own history across the cosmos, not with light, but with the silent architecture of everything we see. This second method for reading the Cosmic Palimpsest involves mapping the universe on its grandest possible scale, charting the vast cosmic web of galaxies, clusters, and immense, empty voids. This sprawling structure is the grown-up version of the tiny seeds we see in the cosmic microwave background. By conducting massive surveys of the sky, projects like the Sloan Digital Sky Survey have painstakingly mapped the positions of millions of galaxies. They reveal a universe woven into a delicate filamentary structure, a great cosmic spiderweb where galaxies cluster along dense strands, connected at nodes by enormous galaxy clusters, and separated by vast, empty caverns of nothingness. This entire architecture is a fossil record of gravity's work over billions of years. The subtle gravitational pull of dark matter, an invisible substance that makes up most of the universe's mass, provided the scaffolding. Ordinary matter, the stuff of stars and planets, was then drawn into these dark matter wells, eventually forming the galaxies we observe today. To read this fossil record, astronomers rely on a crucial tool called redshift. As the universe expands, the light from distant galaxies is stretched, making it appear redder. The farther away a galaxy is, the more its light is redshifted. By measuring this redshift for countless galaxies, we can determine their distances and create a three-dimensional map of the cosmos, a map that also functions as a timeline. One of the most powerful rulers etched into this map is a phenomenon known as Baryon acoustic oscillations. In the early universe, pressure waves like cosmic sound waves rippled through the hot plasma. These waves froze in place when the cosmic microwave background was released, imprinting a preferred scale on the distribution of matter. Today, we can still see this faint, fossilized echo. Galaxies are slightly more likely to be separated by a specific distance, a relic of those ancient sound waves. By measuring this standard ruler at different cosmic epochs, we can track how the expansion rate of the universe has changed over time, revealing the competing influences of dark matter, which pulls things together through gravity, and dark energy, which pushes space apart. The overall shape of this web beautifully matches predictions from our leading model of cosmology. Yet, there are subtle discrepancies that hint at a deeper, overwritten past. The immense voids between the galactic filaments appear to have sizes and distributions that are slightly off from what our models predict. Some theorists wonder if these cosmic empty spaces are not entirely empty, but instead hold faint imprints from a time before the Big Bang, perhaps scars from collisions between universes in a greater multiverse. What stories could these great cosmic deserts, these voids of apparent nothing, be whispering to us? Their silence might be the most profound message of all, one that leads us to an even more elusive cosmic signal, the faintest ripples in the fabric of spacetime itself. The silent architecture of the cosmic web is one thing, but what about the sound? A third method for reading the universe's hidden history listens for the faintest vibrations in the fabric of reality itself, the ripples of spacetime known as gravitational waves. These are not made of light, but are literal waves in the geometry of the cosmos, generated by the most violent events imaginable. When two black holes, each containing the mass of dozens of suns, spiral into a final, cataclysmic merger, they shake the universe, sending out tremors that travel at the speed of light across billions of light years. The first direct detection of these waves in 2015 by the LIGO Observatory was a monumental achievement, opening a brand new sense with which to perceive the cosmos. This is a sense of hearing. Unlike light, which can be absorbed, scattered, or distorted by dust and gas, gravitational waves pass through the universe almost completely unaffected. They are pristine messengers, carrying a clean, unaltered story from the moment of their creation. Scientists decode this story by analyzing the intricate patterns in the waves. The specific chirp of a gravitational wave signal reveals the masses of the colliding objects and their dynamics, telling us whether we are witnessing the merger of two black holes or two ultra-dense neutron stars. This new window allows us to probe epochs that are completely dark to traditional telescopes. The cosmic microwave background gives us a snapshot of the universe at 380,000 years old, but gravitational waves can theoretically take us back further, to the very first fractions of a second after the Big Bang. Future observatories, like the space-based LIS mission, will be sensitive enough to hunt for a background hum of primordial gravitational waves. These would be the faint echoes from the universe's period of inflationary expansion, a time when spacetime itself was stretched to cosmic proportions in an instant. Detecting this signal would be like listening to the birth cry of the cosmos, potentially offering evidence for theories of a multiverse or a cyclic universe that endlessly repeats. The power of this new astronomy was spectacularly demonstrated in 2017, with an event catalogued as GW170817. For the first time, astronomers detected both gravitational waves and a flash of light from the same source, the merger of two neutron stars. This multi-messenger event allowed scientists to independently measure the expansion rate of the universe and to witness the creation of heavy elements like gold and platinum, forged in the incredible furnace of the collision. So how can waves from black holes tell us about the universe's infancy? Because the earliest moments of reality were likely filled with similar, unimaginable violence, phase transitions and cosmic strings that would have sent their own shudders through spacetime. By building ever more sensitive listening devices, we are tuning our ears to the static of creation, hoping to hear the whispers of time before time. But if these colossal events write their history in spacetime ripples, they also write it in the very elements that make up our world, leaving behind a chemical record etched into the oldest stars. The violent birth of elements in colliding neutron stars writes a recent chapter, but the very first chemical sentences were inscribed in the universe's opening minutes. This fourth method for reading the Cosmic Palimpsest looks at the primordial recipe for the lightest elements. In the first few minutes after the Big Bang, the entire cosmos was a searingly hot nuclear fusion reactor. Protons and neutrons collided and fused, creating the first atomic nuclei, primarily hydrogen and helium, with trace amounts of lithium and deuterium. This process, called Big Bang Nucleosynthesis, lasted only a short time before the expanding universe cooled and froze these elemental abundances in place. They became a permanent chemical fingerprint of the universe's earliest conditions, a signature we can still measure today. The brilliant physicist George Gamow and his colleagues first predicted this primordial cooking process. They realized that the relative amounts of these light elements depended critically on how dense the universe was in its first few minutes, and on the number of different types of lightweight particles, like neutrinos, flying around. Think of it like a time capsule. The specific ratio of hydrogen to helium, or the tiny amount of lithium, acts as a cosmic thermometer and barometer for that frantic initial period. To read this ancient recipe, astronomers use powerful spectrographs on telescopes like Hubble. These instruments break apart the light from the most ancient stars we can find, known as metal-poor halo stars. These stellar elders formed from nearly pristine gas, so their atmospheres preserve a remarkably pure record of the primordial element mix. By analyzing their light, we can measure the abundances of elements forged only in the Big Bang. For the most part, the predictions match the observations beautifully, a stunning confirmation of our standard model. The amount of deuterium we see, for instance, acts as a supremely sensitive baryometer, telling us precisely how much ordinary matter exists in the cosmos. Yet, there is a glaring and persistent problem, the lithium problem. The universe contains only about 1/3 of the lithium-7 that our models predict should exist. This is not a small error, it is a major discrepancy. What could have caused this missing lithium? The answer might lie in overwritten physics. Perhaps unknown particles were present, like certain types of dark matter that decayed and altered the nuclear reactions. Maybe the early universe was not perfectly smooth, but had dense lumps and thin regions, an inhomogeneous model that would change the fusion yields. Or, some theorists speculate, this chemical anomaly is a residue from a prior cosmic phase, a ghost from a universe that existed before our own in a cyclical cosmos. The number of neutrino flavors also plays a crucial role, as more types would have made the universe expand faster, changing how long fusion could occur and altering the final helium abundance. Why do these seemingly mundane amounts of helium and lithium hold such profound clues? Because they are the only direct physical relics we have from before the first stars ever shone. They are the chemical bedrock upon which all later cosmic history was built. Any deviation in their expected ratios is a potential whisper from a time before time, a hint that our universe's first page was written over an even more ancient text. This search for elemental ghosts leads us to look for another kind of background glow, one not in microwaves, but in the infrared, a faint light that tells the story of all the stars that have ever lived. That faint elemental fingerprint leads to a different kind of glow, a cosmic afterglow written not in chemistry, but in pure light. Across the entire sky, there exists an incredibly dim background of infrared radiation, a diffuse light that is the summed emission from every star and galaxy that has ever existed, their light stretched and faded by the expansion of the universe. This is the cosmic infrared background, and it is the fifth great method for reading the Cosmic Palimpsest. While the cosmic microwave background is a snapshot of the infant universe, the cosmic infrared background is a blurred family photo of all its stellar generations. It is the accumulated light of creation, a direct record of the total star formation that has ever occurred. To map this background, astronomers use space telescopes like Spitzer and Herschel, which are specially designed to see in the infrared and are placed far from Earth's own warm, glowing atmosphere. The challenge is monumental. They must first subtract the brilliant foreground light from our own solar system's dust and from the Milky Way's stars, a process like trying to hear a whisper in a roaring stadium. What remains is a faint, uneven tapestry, a map of anisotropies or fluctuations in this infrared glow. These subtle brightness variations are not random. They are the ghostly imprints of the very first structures to ever switch on. The patterns in this light encode the timing of the Epoch of Reionization, when the first stars and galaxies lit up, and their intense radiation tore apart the neutral hydrogen gas that filled the cosmos. By analyzing the statistical properties of these fluctuations, their power spectrum, scientists like Alexander Kashlinsky can infer the properties and distribution of those first luminous objects. They are searching for a specific signal within this background, a particular pattern of clumpiness that could be the signature of population, 3 stars. These were the universe's very first stars, hypothetical giants made only of hydrogen and helium, hundreds of times more massive than our Sun, burning ferociously and dying young in spectacular supernova. Their direct light is too faint to see individually, but their collective glow might be preserved in the large-scale patterns of the cosmic infrared background. To isolate these ancient contributions, researchers perform a kind of cosmic cross-examination. They cross-correlate the infrared background map with other data, like the cosmic microwave background. If a hot spot in the infrared aligns in a specific way with a cold spot in the microwave background, it can reveal how the first star's energy interacted with the ancient cosmos. They also cross-reference with X-ray maps, looking for hints that some of the infrared fluctuations might be from the accretion disks of primordial black holes, another potential relic from the universe's earliest moments. The anomalies are the most exciting part. Excess fluctuations at certain angular scales, clumpiness that is too strong to be easily explained by known galaxies, could be the remnant signal of something far more exotic. Could it be the faint glow from the decay of dark matter particles, or perhaps an imprint from a pre-inflationary phase of the universe, a time when the cosmic parchment was first being prepared? This dim infrared light is more than just a record of early stars. It is a deep storage device for the universe's lost memories, a testament to every light that ever was. And this search for the ghosts of the first structures inevitably points us toward the invisible architect of the cosmic web, the dark matter that holds the entire story together. That invisible scaffolding, dark matter, holds the deepest and most pristine memories of the cosmos, while ordinary matter, the stuff of stars and planets, gets blown about by the winds of supernova and the violence of galactic collisions. Dark matter remains aloof. It does not emit, absorb, or reflect light. It feels only gravity's pull, making it the universe's most faithful archivist. Its distribution across the cosmos today is a direct, if ghostly, map of the initial conditions set during inflation. Those quantum seeds, stretched to cosmic proportions, determined where dark matter first began to clump, and its gravitational wells then guided all the visible structure we see. The pioneering work of astronomers like Vera Rubin revealed this hidden architecture. By measuring how fast stars orbit the centers of galaxies, she found their speeds did not drop off with distance as expected. Instead, they remained constant, a clear sign that the galaxies were embedded within vast, massive halos of something unseen, dark matter. This invisible substance outweighs ordinary matter by a factor of about 5 to 1, making it the dominant gravitational force in the universe. To understand how this archive was created, we must go back to the universe's first moments. In the searing heat of the Big Bang, dark matter particles were likely created and then annihilated with their antiparticles. As the universe expanded and cooled, a process called freeze-out occurred. The particles simply became too spread out to find each other, leaving behind a relic population that permeates the cosmos to this day. The exact nature of these particles is one of physics' greatest mysteries. Candidates like WIMP, or weakly interacting massive particles, emerge from theories like supersymmetry, which posits a partner particle for every known particle in the Standard Model. Discovering which particle is correct would tell us not just what dark matter is, but potentially what physical laws operated at energies far beyond what any particle collider on Earth can reach. This is where cosmic archaeology becomes active. We can map this dark matter scaffolding using a phenomenon called weak gravitational lensing. The immense gravity of dark matter clumps warps the fabric of spacetime, bending the light from galaxies behind it. This creates tiny, subtle distortions in the shapes of millions of distant galaxies, like looking through a vast, lumpy pane of glass. By statistically analyzing these distortions, we can reconstruct a three-dimensional map of the dark matter distribution, tracing its growth over billions of years. Some of the most compelling evidence comes from cosmic collisions like the famous Bullet Cluster. Here, two galaxy clusters have slammed into each other. The ordinary matter, in the form of hot gas, was slowed by drag and now sits between the clusters. But the dark matter, which does not interact with itself or the gas, passed right through. By using gravitational lensing, astronomers mapped the cluster's total mass and found it was centered on the galaxies, not the gas. This proved dark matter is not only real but collisionless, its distribution sculpted solely by gravity from the very beginning. How does this collisionless nature make dark matter such a perfect record keeper? Because its structure is not erased or scrambled by the messy astrophysics that constantly rewrites the history of visible matter. The patterns in its cosmic web may therefore contain whispers from before the Big Bang. Some models of a cyclic universe, where our cosmos is born from the collision of previous universes, predict specific signatures in the dark matter distribution, subtle statistical anomalies in how it clumps on the very largest scales. So, when we map the dark matter, we are not just looking at an invisible skeleton. We are reading a text that has remained largely unedited for nearly 14 billion years. It is the permanent ink of the Cosmic Palimpsest. The silent, pristine record of dark matter points toward a past even more ancient than our Big Bang. What if our universe is not a single, unique creation, but merely the latest chapter in an endless cosmic story? This is the radical proposal of cyclic universe models, where the cosmos undergoes perpetual cycles of expansion, contraction, and rebirth. In this view, the Big Bang was not the absolute beginning, but a transition, a great turning of the page. With each new cycle, the universe is reborn from the ashes of its predecessor, its history partially erased and overwritten, yet never completely wiped clean. Theoreticians like Paul Steinhardt propose that just as our cosmic palimpsest holds layers from our own universe's past, it might also contain ghostly imprints from a universe that existed before our own. The evidence for this staggering idea could be hidden in data we are already collecting. The profound uniformity of the cosmic microwave background, for instance, is a cornerstone of the inflationary theory. But cyclic models offer an alternative explanation. In an ekpyrotic scenario, our universe exists as a three-dimensional membrane, or brane, floating in a higher dimensional space. A collision with a neighboring brane could provide the immense energy needed to spark our cosmic cycle, naturally creating a smooth and uniform universe without requiring a period of hyper-fast inflation. This collision would avoid the problematic singularity of a traditional Big Bang, leading to a bounce from a previous state of contraction. So, what kind of signatures would a previous cycle leave behind? One potential clue is in the gravitational wave background. While inflation predicts a specific red tilt in the spectrum of these primordial ripples, many cyclic models predict a blue tilt, meaning more power on smaller scales. Future observatories like LISA could detect this distinct fingerprint. Another key area is the cosmic microwave background's polarization. The search for primordial B modes is a primary goal of cosmology. But what if we don't find them where inflation says we should? A telling absence of these specific patterns at certain scales could be a powerful argument for a cyclic universe, as the physics of the bounce would produce a different signature. Even the large-scale distribution of galaxies might hold a statistical anomaly, a faint concentric pattern or a specific type of non-Gaussianity imprinted by the geometry of the prior cycle's contraction. The challenges are immense, as these signals are incredibly subtle and often mimic effects from within our own cosmic timeline. Even the persistent Hubble tension, the disagreement over the universe's current expansion rate, could be a symptom of an overwritten past, a relic influence from a previous cycle subtly altering how structures form. The idea that our entire cosmos is just one volume in an infinite library of universes forces us to reconsider every anomaly. Is the lithium problem not a flaw in our nuclear physics, but a fossil from a different cosmic recipe? Are the cold spots in the CMB not statistical flukes, but bruises from a long-forgotten collision? The search for these echoes across cycles is the ultimate act of reading the Cosmic Palimpsest, looking for words written in a universe that died before our own was born. And this search for a pre-Big Bang history brings us directly to one of the most pressing mysteries in modern cosmology, a discrepancy that threatens to rewrite our cosmic story, the deepening puzzle of the Hubble constant. This growing puzzle, the Hubble tension, is a crack in the foundation of modern cosmology. Two different ways of measuring how fast the universe is expanding are giving us two different answers. One method looks back to the very beginning, using the cosmic microwave background as its guide. The other looks at the relatively recent universe, observing the steady glow of exploding stars in our galactic neighborhood. They should agree, but they do not. The CMB method, which relies on our standard model of cosmic history, gives us one number for the expansion rate. The local method, using Type Ia supernova and pulsating stars called Cepheid variables as cosmic yardsticks, consistently gives a larger, faster number. This is not a small statistical fluke. The discrepancy has now reached a confidence level that makes it incredibly hard to ignore. A 5 sigma tension that keeps cosmologists like Adam Rees awake at night. The CMB measurement is a look back. It sees the infant universe and then extrapolates forward 14 billion years, assuming the standard lambda CDM model has governed the cosmos throughout its entire life. This model includes dark energy, dark matter, and a specific, smooth history of expansion. The local measurement from projects like SH0ES is more direct. It builds a cosmic distance ladder, carefully calibrating the true brightness of supernova to measure how fast galaxies are receding from us right now. The fact that these two powerful, independent methods disagree suggests that our extrapolation is wrong. The standard model's history of the universe may be missing a chapter. Perhaps there was a brief, early phase of accelerated expansion driven by a form of early dark energy that tweaked the universe's expansion rate just enough to throw off the CMB's prediction. Or maybe the primordial universe was not as perfectly smooth as we assume. Small initial inhomogeneities, density variations left over from a pre-Big Bang era, could have created a local underdensity, a cosmic void that makes our neighborhood expand a little faster than the cosmic average, fooling our local measurements. Other proposed solutions delve into the nature of fundamental particles, suggesting that neutrinos might have unexpected interactions, or that dark energy evolves in a way we have not accounted for. Some even propose modifications to Einstein's theory of gravity itself. The implications for the cosmic palimpsest are profound. If the Hubble tension is real and not a systematic error, it means the foundational text of our universe, the story written in the CMB, has been misinterpreted. A layer of writing from a forgotten epoch, an overwritten phase of rapid expansion or a relic in homogeneity, is subtly altering the meaning of the cosmic story we thought we knew. This tension is more than a numerical puzzle. It is a potential whisper from a time before the cosmic microwave background was set, a clue that our universe's history is even richer and more complex than we imagined. And this search for forgotten chapters inevitably draws us toward the most expansive idea of all, a cosmos of cosmoses, where our entire universe is just one bubble in an infinite, frothing sea of reality. The Hubble tension's crack in our cosmic story widens into an even more profound possibility, that our entire universe is just one accidental bubble in an infinite, frothing multiverse. This is the theory of eternal inflation, proposed by physicist Alan Guth. It suggests that the explosive expansion which shaped our early cosmos never truly stopped everywhere. Instead, it continues eternally in a background sea of space, sporadically giving birth to new bubble universes, each with its own random laws of physics. Our observable cosmos, with its specific constants and particles, would simply be one such region where inflation happened to slow and congeal into the familiar reality we know. Within this staggering framework, the history of our universe could be overwritten not just by its own past cycles, but by encounters with entirely separate cosmic realms. The quantum fluctuations that seeded our galaxies were not the only ones. Other, more dramatic fluctuations in the inflating background could have nucleated new bubbles. Picture a pot of water coming to a rolling boil, with new bubbles constantly forming, expanding, and sometimes, just sometimes, colliding. Researchers like Matthew Klebin use sophisticated simulations to model what such a collision would look like from inside our bubble. The impact would be a cataclysmic event, sending a shockwave through the fabric of our nascent cosmos. This collision would not create a hole in the sky, but it would leave a distinct imprint on the cosmic microwave background. The energy released would slightly heat the plasma in a specific, disk-like region on the CMB sky, leaving behind a telltale signature, a circular cold spot surrounded by a warmer ring. The search for these cosmic bruises is a monumental challenge. The signals would be incredibly faint and buried in the noisy foreground of our own galaxy's emission. Distinguishing a true bubble collision imprint from a random, statistical fluctuation requires exquisite precision and clever data analysis. Yet, some cosmologists look at certain anomalies, like the famous CMB Cold Spot, or the perplexing large-scale alignment nicknamed the Axis of Evil, and wonder if these are not mere flukes, but the faded scars of a long-ago encounter with another universe. Beyond the CMB, the violent process of bubble formation itself could leave another kind of record. When a new bubble universe forms, its walls are energetic membranes expanding at nearly the speed of light. The collision of these walls, or their gravitational dynamics, would generate a storm of gravitational waves, creating a stochastic background hum that future observatories might one day detect. This leads to a deep philosophical puzzle known as the Measure Problem. In an infinite multiverse where every possible physical reality exists somewhere, how do we calculate the probability of anything, including our own existence? It forces us to ask if the fundamental constants we measure are truly fundamental, or merely local bylaws in our particular cosmic neighborhood, overwritten from a much vaster and more varied cosmic history. The quest to find these imprints is the ultimate test of the palimpsest idea. Are we reading subtle clues that point to a reality beyond our own cosmic horizon? This search for echoes from other bubbles pushes our understanding to its absolute limit, into the realm where spacetime itself loses its meaning, the domain of quantum gravity. At the very threshold of time, the universe was a realm of pure potential. This is the Planck epoch, the first fleeting fraction of a second after the Big Bang, where the energies were so immense that gravity itself became a quantum force. Here, the smooth continuum of spacetime we know dissolved into a seething, chaotic foam, a bubbling sea of virtual black holes and wormholes popping in and out of existence. In this frantic, foundational moment, the laws of physics as we understand them break down, and the universe's origin story was likely written in a language we are still struggling to decipher, the language of quantum gravity. This is the deepest, most overwritten layer of the Cosmic Palimpsest, a text inscribed not on parchment, but on the very fabric of reality at scales a trillion times smaller than an atom. The central challenge is that this epoch is permanently veiled from our direct observation, its energy so far beyond what any particle collider could ever reach. Yet, its ghost may linger in the cosmic data we can collect today. Theories like loop quantum gravity, championed by physicists like Carlo Rovelli, propose that spacetime is not smooth and continuous, but is woven from a network of discrete, finite loops. Think of it as the universe's fundamental pixelation. In this view, the Big Bang was not a singular beginning from nothing, but a great bounce from a previous cosmic phase. The information from that prior universe could be encoded in the spin of these tiny loops, a cosmic inheritance preserved through the transition. This leads to a profound possibility that our universe is cyclic not just in its expansion, but in its very quantum structure. The statistical properties of the cosmic microwave background, the specific patterns of its hot and cold spots, could carry the faint statistical imprint of that primordial quantum state. Another compelling idea comes from string theory and the holographic principle. It suggests that all the information describing a volume of space, including the history of everything within it, can be encoded on its two-dimensional boundary, much like a three-dimensional hologram is projected from a flat surface. This AD-CFT correspondence is a powerful mathematical tool that implies information is never truly lost, not even when it falls into a black hole. This directly addresses the black hole information paradox, a puzzle about whether information swallowed by a black hole is destroyed, violating quantum mechanics, or somehow preserved. If information is eternally safe on a hidden surface, then the entire history of our cosmos from the Planck epoch onward is permanently archived. The question becomes, how do we read this archive? The most promising window might be through the oldest light we have. The hunt for primordial B-mode polarization in the cosmic microwave background is not just a search for inflationary gravitational waves. Some models suggest that the specific characteristics of these spacetime ripples, a slight deviation from the predictions of simple inflation, could reveal the fingerprints of quantum gravity processes. Did spacetime foam leave a specific statistical signature on these waves? Furthermore, the entanglement entropy of the universe, a measure of how quantum particles in distant parts of the sky are mysteriously connected, might also hold a clue. The pattern of this large-scale entanglement could be a fossil from the universe's first moments, when everything was intimately linked. We can also look for relics from that chaotic era. Primordial black holes, theorized to have formed from dense fluctuations in the early universe, could be such messengers. If they exist, their mass and distribution would tell us about the conditions of the cosmos when they were born, potentially revealing the spectrum of those initial quantum fluctuations. Even ultra-high-energy cosmic rays, the most energetic particles in the universe, could carry traces of physics from near the Planck scale. How can the tiniest scales of physics illuminate the grandest historical narratives? The answer is written in the collisions of black holes. Each merger is a violent experiment in quantum gravity, and the gravitational waves they emit are a clean signal carrying information about the nature of spacetime itself. By analyzing the echoes of these crashes, we are listening for the subtle sounds of a pixelated cosmos. Each gravitational wave signal is a time capsule from a distant, violent event. When two black holes spiral inward and merge, the ripples they create in spacetime carry a precise story. The specific chirp of the wave reveals the object's masses and spins, but it can also tell us about the environment where these black holes were born and the cosmic era they call home. Since the first detection by LIGO, these collisions have become more than just spectacular events. They are unique probes of the high redshift universe, a period difficult to observe with light. By analyzing the population of these mergers, scientists like Vicky Kalodra can perform cosmic archaeology. They use sophisticated population synthesis models, which are complex simulations that track the birth, life, and death of stellar systems across cosmic time. The statistical distribution of black hole masses, for instance, is a powerful clue. A surprising number of black holes detected fall within a mass range that is heavier than expected from standard stellar evolution models. This could mean that many of these black holes were born not from isolated stars, but within dense stellar clusters, where repeated interactions and mergers can build up heavier objects over time. Alternatively, some of these unexpectedly heavy black holes could be the direct remnants of the universe's very first stars, the mythical population 3 stars. These primordial giants would have lived fast and died young, leaving behind black holes that preserve a chemical signature of a universe without heavy elements. The rate of mergers across cosmic time is another critical data point. If the merger rate was higher in the past, it could indicate that the early universe was filled with more of these dense stellar nurseries, painting a picture of a more violent, chaotic youth. To gather enough statistics, scientists are not just listening for individual chirps, but for a persistent hum. This is the stochastic gravitational wave background, a low rumble created by the combined signal of every binary black hole merger that is too distant and faint to be heard individually. It is the integrated sound of cosmic history, a statistical record of how many of these events have occurred over billions of years. The shapes of the wave signals themselves hold further clues. Most binary black holes are expected to have circular orbits, a result of evolving together as a stellar pair. But some detected signals show hints of eccentricity, a distinctive wobble in the waveform. This eccentricity is a telltale sign of a dynamical formation. It suggests these black holes did not grow old together, but were thrown into their fatal dance by a close encounter in a crowded environment like a globular cluster or a galactic nucleus. The hunt is also on for intermediate mass black holes, objects with masses between 100 and 100,000 times that of our Sun. These are considered potential missing links, the seeds from which the supermassive black holes at the centers of galaxies grew. Finding them through their gravitational wave emissions would be a direct window into a very early phase of structure formation. Perhaps the most profound implications come from the outliers, black holes with masses so large or so small they defy conventional explanation. Could a black hole with a mass of 100 suns be a primordial black hole, forged not from a star but from a dense lump of matter in the universe's first second? Such a detection would be revolutionary, pointing to new physics during inflation or even serving as a candidate for dark matter. The gravitational waves from these ancient crashes might even carry subtle imprints related to baryogenesis, the process that created the matter-antimatter asymmetry, if certain theoretical particles were involved. Every ripple is a message, and we are only just beginning to understand the language. What other stories from the universe's violent adolescence are encoded in these silent tremors? This search for gravitational echoes leads us to an even more elusive messenger, one that has been streaming through the cosmos since the first second of time. These silent messengers have been flowing through the cosmos since the universe was just 1 second old. Billions of ghostly neutrinos pass through your body every second, a faint whisper from the Big Bang itself. This is the cosmic neutrino background, a relic sea of particles that decoupled from the primordial soup, even before the cosmic microwave background was created. Detecting this background directly is one of the greatest experimental challenges in all of physics, as these neutrinos now possess incredibly low energy, moving at speeds far slower than their freshly born counterparts. Yet their influence is written across the cosmos. The work of physicists like John Bockall was crucial in proving we could even detect neutrinos from cosmic sources. His calculations of the solar neutrino flux led to the famous Homestake experiment, which first revealed that neutrinos change flavors as they travel. a phenomenon called neutrino oscillation. This discovery told us that neutrinos have mass, a fact not originally part of the Standard Model, and it opened the door to understanding how these particles shaped the universe. Their impact is profound. During Big Bang Nucleosynthesis, the number of neutrino flavors directly influenced how fast the universe expanded, which in turn set the final abundance of helium we see today. The presence of these light, fast-moving particles also affected the growth of the cosmic web. Because neutrinos barely interact with matter, they stream freely out of dense regions, effectively smoothing out the earliest clumps of dark matter and slowing the formation of the very first structures. We can see this ghostly handiwork in the cosmic microwave background. The precise pattern of the damping tail, the sharp drop in temperature fluctuations on very small scales, is a direct record of how much the free streaming of neutrinos erased these tiny primordial wrinkles. Any anomaly in this pattern could be a whisper of something beyond the standard 3 neutrinos. The hypothetical sterile neutrino, a particle that interacts only through gravity, would have dramatically altered this early smoothing, leaving a distinct signature that cosmologists are actively hunting for in galaxy survey data. The greatest goal, however, is to capture one of these relic neutrinos directly. Future experiments like PTOLEM plan to use a spectacularly sensitive method involving tritium, a radioactive form of hydrogen. The idea is to watch for a unique event, a relic neutrino striking a tritium nucleus and causing it to decay, releasing an electron with a specific, telltale energy. Succeeding in this would be like capturing a ghost. It would confirm a fundamental prediction of our standard cosmic story. But if the properties of these captured neutrinos deviate from our expectations, if their energies or flavors are wrong, it could point to a non-standard history. Perhaps the universe underwent a low-temperature reheating phase after inflation, leaving a colder neutrino background, or maybe a significant lepton asymmetry. An imbalance between matter and antimatter in the neutrino sector exists, rewriting the conditions of the universe's first second. These nearly undetectable particles, the universe's most aloof archivists, could hold the key to understanding the very first overwritten page of our cosmic history. And if these ghostly streams can shape galaxies, what other invisible forces are writing their stories across the cosmos? Perhaps through vast, primordial magnetic fields woven into the fabric of space itself. These invisible threads of force are woven through the cosmos itself. Primordial magnetic fields are hypothesized to be a fundamental, if faint, feature of the universe, present from its first moments and stretched to intergalactic scales by the universe's expansion. Unlike the magnetic fields of stars and galaxies, which are localized and dynamic, these ancient fields would be a pervasive background, a fossil force field that has subtly guided cosmic evolution for billions of years. The mystery of their origin takes us back to the universe's most extreme epochs. One compelling idea is that they were generated during a phase transition, a moment when the fundamental forces of nature split from a single, unified force. As the cosmos cooled, this splitting could have created defects in spacetime, much like cracks forming in ice, releasing immense energy that seeded the first magnetic fields. Another possibility lies in the heart of inflation itself. The same quantum fluctuations that seeded galaxies could have also created fluctuations in electromagnetic fields, which were then inflated to cosmic proportions. This process, known as the Harrison mechanism, suggests these fields were born from the very same quantum jitters that gave rise to all structure. But why would these fields persist? The early universe was a hot, dense plasma, a perfect conductor that could trap and preserve magnetic field lines, freezing them into the fabric of space as it expanded. These fields, though incredibly weak by human standards, could have played a crucial role as cosmic architects. During the formation of the first stars and galaxies, their subtle pressure could have provided an extra push, helping to collapse gas clouds or, conversely, preventing the smallest clumps of dark matter from ever forming stars at all. They would have influenced the Epoch of Reionization, guiding the powerful radiation from the first stars and galaxies as it ionized the neutral hydrogen fog of the early cosmos. The most tantalizing evidence for these ghostly fields comes from how they manipulate light. As light from distant, brilliant objects called blazars travels across billions of light years to reach us, it passes through these vast magnetic fields. This journey causes a phenomenon known as Faraday rotation, where the magnetic field twists the orientation, or polarization, of the light waves. By meticulously measuring this rotation in the light of many blazars, astronomers can map the strength and coherence of magnetic fields in the seemingly empty space between galaxies. Finding a coherent magnetic field in a void, a region that has never hosted a galaxy, would be a smoking gun for a primordial origin. The cosmic microwave background also holds potential clues. Primordial magnetic fields would have created tiny, swirling motions in the primordial plasma, which in turn would have imprinted a specific, non-Gaussian pattern on the CMB's polarization. This creates a unique type of B-mode polarization, a signature distinct from the one created by inflationary gravitational waves. If we detect this specific magnetic fingerprint, it would not only confirm the existence of these ancient fields, but could also point to specific models of inflation or other exotic physics from the universe's first instance. The hunt is also on in the realm of ultra-high-energy cosmic rays. These mysterious, immensely powerful particles are deflected by magnetic fields as they travel through space. The patterns of their arrival directions could, in theory, reveal the structure of the intergalactic magnetic fields that guided them on their long journey. What can these invisible force fields, these cosmic fossils of force, reveal about the universe's most formative events? Their detection would be a direct line back to an era before the first atoms even formed, a hidden chapter written in magnetism. This search for magnetic ghosts leads us to examine the very light from the most distant cosmic beacons, the quasars whose absorption lines may hold the final, definitive evidence. That brilliant light from distant quasars acts as a cosmic flashlight, illuminating everything in its path. As this intense beam travels billions of light years to reach our telescopes, it passes through countless clouds of primordial gas and the halos of young galaxies. Each cloud leaves a unique fingerprint on the light, a series of dark absorption lines in the quasar's rainbow-like spectrum. These lines are a direct chemical assay of the intervening matter, revealing its composition, temperature, and density at a specific moment in cosmic history. It is as if we have been given millions of tiny, sealed vials of the ancient universe, each one containing a sample of space from a different epoch. Astronomers like Wallace Sargent pioneered the use of these cosmic probes, using them to map the large-scale structure of the universe in a way that is impossible with traditional telescopes. The most common pattern is the Lyman alpha forest, a dense, beautiful thicket of absorption lines created as the quasar's light passes through the diffuse neutral hydrogen that fills intergalactic space. The sheer number of lines reveals the cosmic web in stunning detail, with each dip in the spectrum corresponding to a different filament or knot of that vast, invisible scaffolding. By measuring the redshift of each line, we can reconstruct a three-dimensional map of this gaseous structure, turning a single beam of light into a core sample of the cosmos. But the story does not end with hydrogen. Rarer, so-called metal lines from elements like carbon, oxygen, and silicon appear when the light passes through the enriched gas surrounding galaxies. These lines tell a story of cosmic pollution, of generations of stars living and dying, seeding the void with the heavy elements forged in their cores. This is how we trace the rise of the first galaxies and their powerful winds, which blew gas and metals far out into the emptiness. The most dramatic systems are the damped Lyman alpha absorbers, incredibly dense clouds of neutral hydrogen that are the direct progenitors of modern galaxies. These are the cosmic nurseries where gas was cool and dense enough to collapse and form the first stars, and they provide a fossil record of galaxy assembly. To read these spectral fingerprints, astronomers use high-resolution spectrographs on giants like the Keck and very large telescopes, instruments so precise they can detect a shift in the lines equivalent to the speed of a person walking. This precision allows for breathtaking tests of fundamental physics. By comparing the spacing of lines from different elements in these ancient clouds, scientists can hunt for any evidence that the fine structure constant, a number governing the strength of electromagnetism, was different in the past. A detected variation would be revolutionary, suggesting our laws of physics are not eternal, but could be the local outcome of a phase transition or a domain wall from a prior cosmic era. Even the relative amounts of elements hold profound clues. The abundance of deuterium, a heavy form of hydrogen, in these pristine clouds is a sensitive baryometer, confirming how much ordinary matter exists. Anomalies in its measured value could point to non-standard nucleosynthesis or even exotic interactions with dark matter in the early universe. Some search for the ghostly signature of population, 3 stars in the unique chemical pattern they would have imprinted on their surroundings, a single, clean line of pure oxygen or carbon without the pollution of later generations. How do these spectral lines encode billions of years of history? They are a layered text, with the deepest redshifts showing the universe in its simple, youthful state, and the more recent ones revealing the increasingly complex, chemically enriched cosmos we inhabit today. Each line is a time capsule, a fleeting shadow that speaks of the vast, invisible architecture of reality. And as we decode the messages written in this ancient light, we are inevitably drawn to another pervasive signal, a faint radio whisper that fills all of space. This faint radio whisper is the cosmic radio background, a diffuse static that fills the entire sky. It is the integrated hum of countless distant processes, a chaotic chorus of synchrotron radiation from electrons spiraling around magnetic fields, the soft crackle of free emission from hot gas, and the gentle warmth of spinning interstellar dust. Yet, within this seemingly random noise, there are strange anomalies, whispers that do not fit the standard story. Telescopes like LOFOR and data from projects like ORCA-DE2 have revealed an unexpected excess of radio waves at very low frequencies. The sky is simply brighter than our best models of known astrophysical sources can explain. This unexplained glow is a profound puzzle. What could be generating this pervasive, extra radio light? One possibility is the decay of dark matter. If certain theoretical dark matter particles are unstable, their slow disintegration across cosmic time would release energy, some of which could manifest as this diffuse radio excess. Another explanation points to an unseen population of the very first stars, their intense radiation creating a global signal that has been stretched and faded into the radio band. Or, most radically, this could be a residue from a previous cosmic cycle, a fossil energy field that survived the transition into our own universe. Radio astronomers like Tessa Wernstrom hunt for these primordial components by performing a kind of cosmic cross-examination. They take detailed maps of the radio sky and cross-correlate them with maps at other wavelengths, like the cosmic infrared background or the cosmic microwave background. If a pattern of radio brightness aligns in a specific way with a structure seen in infrared light, it can isolate the contribution from early star-forming regions. The statistical properties of the radio fluctuations, their power spectrum, are meticulously modeled. The standard astrophysical foregrounds, like our own galaxy's emission, are carefully subtracted. What remains are anomalies like the ORCA-DE2 excess, a signal that stubbornly resists conventional explanation and points toward new physics or a forgotten chapter in cosmic history. Spinning dust emissions, where tiny, rotating grains in interstellar space generate a specific type of radio signal, are one piece of this puzzle. Another exotic source could be radio waves from the accretion disks of primordial black holes, theoretical objects that may have formed in the universe's first instance. This search for a radio palimpsest is deeply intertwined with 21 Centimeter Cosmology, which aims to probe the dark ages before the first stars. The EDGES experiment made a stunning claim, detecting what appeared to be an absorption signal in the radio spectrum, a dip that was much deeper than models predicted. If real, this could be evidence of the first stars cooling the primordial hydrogen gas. But the cooling required is so extreme that some physicists suggest it points to an interaction between dark matter and ordinary matter in the early universe, a process that would have left a permanent, if subtle, scar on the radio background. What ultimate secrets does this radio universe hold about our origins? The answers may be written not just in our cosmos, but in the static from countless others. That vast radio static might be the static of countless other realities. The multiverse theory proposes that our cosmos is not the only one, but merely a single page in an infinite cosmic library, a single bubble in a frothing sea of eternal inflation. Within this staggering framework, our universe becomes the ultimate palimpsest, its deepest layers potentially bearing the faint scars of interactions with entirely separate cosmic realms. The mechanism for this is eternal inflation, a theory developed by physicists like Andre Linde. It suggests the vacuum energy that drove our universe's initial explosive growth never truly vanishes everywhere. Instead, it persists in a background state, continuously spawning new bubble universes, each with its own random, crystallized laws of physics. Our entire observable cosmos, with its specific constants and particles, is just one such region where this inflation slowed and congealed into the familiar reality we know. In this eternal churn, these bubble universes can, on rare occasions, collide. Such a collision would be a cataclysmic event, sending a shockwave through the fabric of our nascent cosmos. This would not create a hole in the sky, but it would leave a distinct, circular imprint on the cosmic microwave background. The energy released would slightly heat the plasma in a specific, disk-like region, potentially leaving behind a telltale signature, a circular cold spot surrounded by a warmer ring. Cosmologists have scrutinized the famous CMB Cold Spot and other large-scale statistical anomalies, wondering if these are not mere flukes, but the faded bruises of a long-forgotten encounter with another universe. The search for these imprints is a monumental challenge, requiring us to distinguish a true collision signal from the noisy foreground of our own galaxy's emission and random statistical variations. Beyond the CMB, the violent process of bubble formation itself would generate a storm of gravitational waves, creating a stochastic background hum that future observatories like LISA might one day detect. The characteristics of this hum, its spectrum and amplitude, could carry the fingerprint of a multiverse, differing from the predictions of simple single-universe inflation. This entire line of inquiry leads to profound philosophical puzzles, most notably the measure problem. In an infinite multiverse where every possible physical reality exists somewhere, how do we calculate the probability of anything, including our own existence? It forces us to ask if the fundamental constants we measure, like the strength of gravity or the mass of an electron, are truly fundamental, or merely local bylaws in our particular cosmic neighborhood. This is where the anthropic principle often enters the discussion, suggesting that we observe these specific constants simply because they are the only ones that allow for the existence of life to observe them. Some theories go even further, suggesting that what we perceive as our three-dimensional universe might be a holographic projection from a two-dimensional boundary, a concept stemming from the AD-SCFT, correspondence in string theory. In this view, the information describing our entire cosmic history, including potential collisions with other universes, could be encoded on that distant, abstract surface. How could we ever hope to test such an ethereal idea? The answer may lie in persistent anomalies. If future, higher precision maps from Planck's successors continue to show certain large-scale statistical inhomogeneities or specific, concentric patterns in the CMB polarization that defy conventional explanation, they could become the strongest evidence yet that our universe's history was overwritten by an interaction with a neighboring realm. The very fact that we can conceive of searching for these echoes pushes the idea of a cosmic palimpsest to its absolute limit, suggesting that the deepest text we can read might not be from our own past, but from a reality entirely beyond our own. How might the existence of other universes reshape our understanding of cosmic history? This leads us to examine the evidence from gamma-ray bursts. A brilliant flash outshines an entire galaxy for a few fleeting seconds. These gamma-ray bursts are the universe's most powerful explosions, cosmic beacons that briefly illuminate the deepest, darkest corners of space and time. Their fleeting light is a message, and in its fading afterglow, we find a detailed chemical assay of the universe's youth. When a satellite like Swift detects a burst, telescopes around the world and in space immediately swivel to catch its afterglow, a fading glow that can linger for hours or days across various wavelengths. This afterglow is not just a dying ember, it is a cosmic probe. As this brilliant light travels through its host galaxy and across vast intergalactic space, it passes through clouds of gas and dust. Each element in these clouds leaves a unique fingerprint, an absorption line, on the afterglow's spectrum. By reading these dark lines, astronomers like Niall Tanvir can determine the chemical composition of the galaxy that hosted the burst, measuring its metallicity, which is the abundance of elements heavier than hydrogen and helium. This single measurement tells a profound story about that galaxy's history, a record of how many generations of stars have lived and died there, seeding it with the elements for planets and life. Long-duration gamma-ray bursts, those lasting more than 2 seconds, are particularly revealing. They are linked to the core collapse of massive, rapidly spinning stars. These are not the quiet deaths of ordinary stars. They are hypernova, cataclysmic events that produce tightly focused jets of energy beaming out from their poles. If one of those jets is pointed at Earth, we see it as a gamma-ray burst. This direct connection to massive stellar death makes GRBs perfect tracers of star formation. Where stars are forming rapidly, you will find massive, short-lived stars, and therefore, you have a chance of seeing a GRB. By measuring the redshift of a burst, we can place it at a specific moment in cosmic history. Compiling these events across time allows us to construct a cosmic star formation history, a graph of how the universe's stellar productivity has risen and fallen over billions of years. These beacons allow us to see further back than ordinary galaxy surveys, probing epochs when the universe was less than 1 billion years old. They act as a backlight, illuminating the diffuse gas of the intergalactic medium. During the Epoch of Reionization, when the first starlight was tearing apart the neutral hydrogen fog of the early cosmos, the light from a high redshift GRB would carry a specific signature of that process. The way its light is absorbed by neutral hydrogen can tell us the precise timeline of when the universe became transparent to ultraviolet light. Some bursts show peculiarities that hint at even more exotic origins. An unusually long and energetic burst could be the signature of a pair instability supernova, the complete annihilation of a supermassive star that leaves no black hole behind. Such an event is a prime candidate for the death of a population 3 star, a mythical first-generation star made only of hydrogen and helium. The detection of a GRB from a galaxy with virtually no heavy elements would be monumental, a direct glimpse into the universe's first stellar generation. Other theoretical possibilities are even more startling. Could a small percentage of bursts be caused by the annihilation of dark matter particles within a star's core, triggering a collapse that would not otherwise occur? Or perhaps the strange distribution of some burst energies points to an overwritten physics, a relic influence from a prior cosmic cycle subtly altering how stars die. These brilliant flashes do more than just mark a stellar death. They illuminate the entire cosmic neighborhood, revealing the architecture and chemistry of the universe during its formative years. They are temporary lighthouses in the cosmic dark, and their fleeting messages are written in the language of elemental creation. What other invisible structures, woven into the fabric of space-time, could be the source of even more profound cosmic flashes? These hypothetical scars could be one-dimensional cracks in the very fabric of space-time. Cosmic strings are theoretical relics, predicted by grand unified theories to have formed during a dramatic phase transition in the universe's first moments. As the cosmos cooled, the fundamental forces are thought to have split from a single, unified force, a process called symmetry breaking. This cosmic freezing could have created defects, much like cracks forming in ice, and cosmic strings are one such possible flaw. Infinitesimally thin but unimaginably dense filaments of pure energy stretching across the universe. A single string might be thinner than a proton, yet a segment just 1 mile long could contain more mass than the entire Earth. These are not strings in a material sense, but flaws in the vacuum of space itself, topological knots that the expanding universe has stretched to cosmic proportions. Their existence would be a direct fossil from an era before the cosmic microwave background was created, a time of unimaginably high energies. If they are real, how would we ever detect such ghostly scars? Their primary signature would be written in gravity. A cosmic string exerts no gravitational pull in the Newtonian sense, but its immense density warps spacetime around it in a unique way. If a string passed between us and a distant galaxy, it would act as a gravitational lens, but not in the familiar, blurring way of a black hole or a dark matter clump. Instead, it would create a perfect, identical double image of the galaxy, a clear line of symmetry in the sky with no distortion. This distinct signature is something astronomers actively search for in deep field images. The dynamics of a network of strings would be even more revealing. As these cosmic filaments stretch and move through the expanding universe, they can intersect, forming loops. These loops are not stable. They oscillate violently and decay by radiating energy in the form of gravitational waves. This creates a continuous, stochastic background of ripples in spacetime, a specific hum that is different from the background produced by merging black holes. Pulsar timing arrays like nanograv, which monitor the incredibly regular pulses from distant neutron stars, are sensitive to this low-frequency hum. A detection of a gravitational wave background with a specific spectral shape could be the long-sought fingerprint of a cosmic string network. The cosmic microwave background also holds potential clues. A moving string would create a step-like discontinuity in the temperature of the CMB, a sharp boundary between a slightly hotter and a slightly colder region, as the string's gravitational field shifts the light's path. While current data from the Planck satellite has placed tight constraints on the possible density of such strings, it has not ruled them out entirely. The connection to other frontier physics is profound. Many models of supersymmetry and brane inflation naturally predict the formation of cosmic strings. In brane inflation, where our universe is a membrane colliding with another in a higher dimensional space, the collision could have spawned these one-dimensional defects. If a future observatory like LISO or a more advanced pulsar timing array detects a signal consistent with strings, it would do more than just confirm their existence. It would provide direct evidence for a grand unified phase transition, a moment when the electromagnetic, weak, and strong forces were one. This would overwrite our understanding of the universe's first instance, revealing a history of violent symmetry breaking etched into the cosmos. How might these cosmic cracks, these frozen relics of a unified force, help explain other persistent anomalies in our cosmic story? This search for gravitational imprints leads us directly back to a fundamental chemical mystery, the stubborn lithium problem. This stubborn lithium deficit is a chemical ghost haunting our cosmic story. The universe's oldest stars, the pristine metal poor halo stars, contain only about 1/3 of the lithium-7 that our most careful models of Big Bang nucleosynthesis predict should exist. This is not a small measurement error. It is a glaring gap in our foundational narrative. According to the Standard Model, the frantic nuclear fusion in the universe's first few minutes should have forged a specific, tiny amount of this light element, a quantity that should be mirrored in the atmospheres of these ancient stellar relics. Yet, when we look, the lithium is simply not there. Where did it go? This lithium problem has forced cosmologists like Brian Fields to consider that the early universe's recipe book was different from the one we assume. Perhaps the cosmos was not perfectly smooth during those first moments. Inhomogeneous nucleosynthesis proposes that the primordial soup had dense lumps and thin regions, altering the nuclear reaction rates and changing the final yield of lithium. Or maybe unknown particles were present, streaming through the plasma and subtly interfering with the fusion process. One compelling candidate is a type of dark matter that decays, releasing energy that breaks apart the delicate lithium nuclei as fast as they form. Other theories venture into even more exotic territory, suggesting that the fundamental constants of nature, like the strength of the gravitational force, were slightly different in that extreme environment, tweaking the nuclear physics just enough to resolve the discrepancy. This search for answers extends beyond stars. Astronomers now use the most powerful telescopes to hunt for lithium's fingerprint in the light from distant quasars, looking for its absorption signature in the pristine gas clouds that have never been polluted by stars. These clouds offer a purer sample than even the oldest stars, which have processed some of their original material. The James Webb Space Telescope, with its incredible infrared sensitivity, is poised to make definitive measurements of lithium in these primordial environments. A confirmation of the low lithium abundance there would be a monumental discovery, forcing a fundamental rewrite of our cosmic history. It would suggest that the universe's first page, the chapter on elemental creation, was overwritten by physics we do not yet understand. This tiny element, lithium, therefore poses one of the biggest problems in all of cosmology because it challenges the very conditions of the universe's infancy. If our understanding of those first few minutes is incomplete, what other chapters of the cosmic story have we misread? This chemical whisper from the dawn of time leads us directly to the next great transition, the moment the cosmos switched on its lights. This second dawn of the universe was a slow and patchy sunrise. For hundreds of millions of years after the Big Bang, the cosmos was a silent, dark fog of neutral hydrogen gas. Then, the first stars and galaxies ignited, and their fierce, ultraviolet radiation began to tear that fog apart, stripping electrons from the hydrogen atoms in a process we call reionization. This was not a single, sudden flash, but a gradual and uneven burning away of the cosmic mist, as bubbles of ionized plasma grew around the first luminous objects, eventually merging to fill the entire universe with the transparent, ionized intergalactic medium we see today. This epoch of reionization, occurring between redshifts of 20 and 6, is a crucial historical layer in the Cosmic Palimpsest. Its story is written in two primary ways. The first is in the polarization of the cosmic microwave background. As the CMB light traveled through this newly ionized plasma, it scattered one last time, imprinting a specific, large-scale pattern on its polarization. This signal acts as a fossil record, telling us the total amount of scattering that occurred and giving us a rough timeline for when reionization happened. The second, and potentially more detailed, record is written in the 21-centimeter line. Neutral hydrogen emits a faint radio signal at a characteristic wavelength of 21 centimeters. By tuning our radio telescopes to search for this signal at different frequencies, which correspond to different cosmic times due to redshift, we can effectively create a three-dimensional movie of the reionization process. We can watch as the first ionized bubbles appear and then slowly grow, mapping the universe's Great Awakening. Experiments like EDGES and LOFOR are on the front lines of this search, building incredibly sensitive antennas in some of the most radio-quiet places on Earth to listen for this ancient whisper. The work of researchers like Judd Bowman with the EDGES instrument has already yielded a stunning and controversial result. They reported detecting what appeared to be an absorption signal in the global 21-centimeter spectrum, a dip that was much deeper and earlier than any model predicted. If this signal is real and not an artifact of fiendishly difficult foreground subtraction, it suggests the primordial hydrogen gas was much colder than expected. One radical explanation is that the gas was cooled through interactions with a form of cold, dark matter. This would be a direct, observable interaction between the visible and dark sectors of the universe, a ghostly hand from the invisible scaffolding reaching out and leaving a mark on the cosmic story. The patchy nature of reionization itself encodes a wealth of information. The size and distribution of the ionized bubbles tell us about the properties of the first light sources. Were they predominantly massive, short-lived population 3 stars, burning ferociously and dying young? Or did smaller, more numerous galaxies provide the bulk of the ionizing photons? The timeline is also critical. If future 21-centimeter tomography reveals that reionization began surprisingly early or progressed with unexpected speed, it could point to non-standard astrophysics. Perhaps the first stars were more efficient at producing ultraviolet light, or maybe there was an additional, exotic source of ionization, such as the decay of primordial dark matter particles or the accretion onto the first black holes. Even the powerful but rare quasars played a role, their intense beamed radiation carving out immense, early bubbles in the neutral hydrogen. Each anomaly in this reionization story is a potential whisper from an even more ancient past. An unexpectedly cold gas temperature, a strangely rapid progression, these could be residues from a pre-inflationary phase, subtle wrinkles in the cosmic parchment that were preserved through the universe's violent birth. What can this story of the universe's second dawn, the moment it became filled with light, ultimately tell us about its absolute first moments? The answer may be that the entire history is written on a distant, two-dimensional surface, a concept at the heart of holographic cosmology. That cosmic library might be written on a two-dimensional surface. The holographic principle is one of the most radical ideas in physics, proposing that our seemingly three-dimensional universe, with all its galaxies, stars, and planets, could be a projection from a vast, distant, two-dimensional boundary. This concept, stemming from the AD-SCFT correspondence discovered by Juan Maldacena, suggests that the information describing everything within a volume of space is entirely encoded on its lower dimensional surface, like a complex hologram. In this view, the Cosmic Palimpsest, the layered history of the universe, is not stored within the cosmos itself, but on its ultimate outer shell. The information about every cosmic event, every overwritten layer, is permanently and safely archived there. This framework fundamentally changes how we might interpret the data we collect. The subtle fluctuations in the cosmic microwave background, those hot and cold spots we map with such precision, may not be primary features. They could be the projected shadows of quantum entanglement and information processing happening on that abstract, two-dimensional boundary. Models like the DSCFT correspondence attempt to apply this holographic logic directly to our own expanding, de Sitter-like universe. They suggest that the physics of the early universe, the period of inflation, can be described by a conformal field theory living on the boundary of spacetime. This means the primordial quantum jitters that seeded all structure were not random, but were the outcome of a precise calculation on that cosmic screen. How could we ever test such an ethereal idea? The key might lie in the statistics of the cosmic microwave background. Our standard models predict that the distribution of hot and cold spots should follow a specific Gaussian pattern. But if the universe is holographic, there could be subtle deviations in this pattern, a specific type of non-Gaussianity in the way the spots are correlated. Future, ultra-precise maps of the CMB from next-generation observatories could search for these statistical fingerprints, looking for a signature that aligns with holographic predictions rather than simple inflation. This search is deeply connected to the black hole information paradox. The holographic principle was born from the realization that the information swallowed by a black hole is not lost, but is encoded on its event horizon, the black hole's two-dimensional surface. This ensures that information is never truly destroyed, a core tenet of quantum mechanics. If this is true for black holes, could it be true for the universe as a whole? The entire cosmic history would be a story where no information is ever erased, only overwritten and preserved on the great cosmic hard drive of the boundary. Another crucial clue is entanglement entropy. In quantum mechanics, particles can become entangled, their fates linked across vast distances. The holographic principle suggests that the spatial fabric of our universe itself is woven from this quantum entanglement. The connections between different regions of the CMB sky could be a fossilized map of the entanglement patterns on the boundary from the universe's first moments. A specific pattern of these connections could be the ultimate proof that we are living in a projected reality. The computational challenges are staggering. Simulating a holographic universe requires solving immensely complex equations on a sphere, a task that pushes the limits of our most powerful supercomputers. Yet, early results are intriguing. Some simulations have shown that a holographic model can naturally produce a universe that looks like our own, with a large-scale structure and an accelerating expansion driven by dark energy, all emerging from the physics of the boundary. How would discovering our holographic nature change the search for lost histories? It would mean that every anomaly, every cold spot and strange alignment is not a flaw in our three-dimensional story, but a crucial piece of data from the two-dimensional code. The great Cosmic Palimpsest would be a single, coherent text after all, and our task would be to learn the language of its projection. This leads us directly to one of the most debated anomalies in the cosmic microwave background, a feature that has resisted explanation for years, the mysterious and immense cold spot. This vast, frigid patch on the cosmic baby picture defies easy explanation. Known simply as the cold spot, it is a sprawling region of the cosmic microwave background significantly colder than its surroundings, a cosmic anomaly that has resisted classification for years. When scientists first identified it in data from the WMAP satellite, its sheer size and profound chill made it a statistical outlier, a feature that should be extraordinarily unlikely in a universe governed by our standard models of inflation. The immediate, conventional suspicion was a supervoid, an immense and mostly empty region of space lying between us and the CMB. As light travels through such a void, it loses energy climbing out of the gravitational well, an effect known as the integrated Sachs-Wolf effect, which would manifest as a cold spot in the ancient light. Yet, when astronomers like Istvan Chaput mapped the galaxy distribution in that direction, they found a void, but not nearly large enough or empty enough to account for the dramatic temperature drop. The observed underdensity, while real, seems insufficient to explain the chill, leaving a gap between prediction and observation. This discrepancy is where exotic physics enters the scene. Theorists like Laura Mersini-Houghton have proposed that the cold spot is not a structure within our universe, but a bruise left by a collision with another universe in the vast multiverse. In the framework of eternal inflation, such a collision would have sent a shockwave of energy through our nascent cosmos, leaving a distinct, circular imprint of altered temperature, a cosmic scar from a realm beyond our own. Another compelling, though equally speculative, idea is that the spot is the signature of a cosmic texture. A texture is a type of topological defect, a knot in the fabric of spacetime itself, formed during a phase transition in the early universe when the fundamental forces were splitting apart. As this knot unraveled, it would have released a burst of energy, creating a localized region of cold in the CMB. If confirmed, a texture would be a direct fossil from an era of grand unification, a time before the cosmic microwave background was even created. Distinguishing between these possibilities is a central goal of modern cosmology. The key lies in the specific pattern the cold spot imprints on the CMB's polarization. A supervoid would create one type of polarization signal, a bubble collision another, and a cosmic texture a third, highly specific signature. Future observatories like the Simons Observatory, with its unprecedented sensitivity, are designed to measure these polarization patterns with exquisite detail, potentially ruling out some theories and providing strong evidence for others. This entire investigation relies on sophisticated statistical tools like Bayesian analysis, which allows scientists to weigh the probability of different models against the stubborn data. The cold spot is more than a curious imperfection. It is a potential window into physics operating at energies far beyond our reach. If it is a texture, it preserves a memory of a phase transition that rewrote the laws of the universe. If it is a multiverse collision, it overwrites our story with a narrative of a broader cosmic reality. This chilly patch challenges us to consider what other ghosts are frozen into the sky, and whether their whispers are linked to other elusive particles, like the hypothetical actions that might permeate the cosmos. These ghostly particles could be the universe's most delicate scribes. Axion-Like Particles, or LPS, are hypothetical, incredibly lightweight entities that barely interact with normal matter. They were first proposed to solve a deep puzzle in nuclear physics known as the strong CP problem, which asks why the strong nuclear force seems to treat matter and antimatter with perfect symmetry. Their existence would elegantly resolve this, but their potential role extends far beyond. Many theories suggest these particles could themselves be the mysterious substance we call dark matter, a vast, unseen ocean flowing through the cosmos. If that is true, then the way they were produced in the universe's first moments would have left subtle scars on the fabric of reality, imprints we might still read today in the ancient light of the cosmic microwave background or in the faint glow of the X-ray sky. The primary way these particles are thought to have been created is through a process called the misalignment mechanism. In the extreme heat of the early universe, the field associated with these particles was frozen at a random value. As the cosmos expanded and cooled, this field began to oscillate, and those coherent oscillations today would manifest as a pervasive, cold sea of Axion-Like particles. Another production method comes from the decay of cosmic strings, those hypothetical one-dimensional defects in spacetime, which would have shed a LPS as they evolved. These production mechanisms are not silent. The oscillations and rare decays of these particles can inject energy into the cosmic plasma at specific times, altering the universe's evolution in ways that leave a permanent record. For instance, if a population of a LPS decayed into photons during the Dark Ages, The extra radiation could have prompted an earlier or more patchy epoch of reionization, a signature that could be etched into the polarization patterns of the CMB. The specific way they scatter light could also create subtle, anomalous features in the cosmic microwave background's polarization, making it appear slightly more isotropic than our models predict. Astronomers are already using these observations to constrain the possible properties of these particles, ruling out certain masses and interaction strengths. The persistent excess of X-rays observed from distant galaxy clusters, for example, could be the long-sought signal of a LPS converting into photons in the presence of strong magnetic fields. These elusive particles might even be the key to solving some of our biggest cosmological puzzles. Their unique properties could have subtly altered the expansion rate of the early universe, potentially explaining the Hubble tension between local and global measurements. They could have interacted with primordial plasma in a way that destroyed some lithium-7, offering a solution to the stubborn lithium problem. Researchers like David Marsh use sophisticated computer simulations to track how these particles would clump under gravity, shaping the large-scale structure of the universe in a way that is distinct from other dark matter candidates. The hunt for these cosmic scribes is accelerating. Next-generation experiments are being built to listen for their whispers. The International Action Observatory, IAXO, will use powerful magnets and exquisitely sensitive detectors to try and convert a LPS in the lab into detectable photons. Ground-based telescopes like CMB-S4 will map the cosmic microwave background with such incredible precision that it could spot the minute spectral distortions or polarization anomalies caused by these particles. If a signal is found, it would do more than just add a new particle to the standard model. It would reveal a hidden chapter in cosmic history, a narrative where these faint, oscillating fields guided the evolution of the cosmos from the shadows, overwriting the simple story we thought we knew. How might the faint pressure from this sea of particles have nudged the entire cosmos into a specific direction, leaving a different kind of mark on the sky? Our motion through the cosmos seems to define a cosmic north. As Earth orbits the Sun and the Sun moves around the galaxy, our entire local group of galaxies is rushing through space. This grand journey creates a distinct signature in the oldest light we can see, the cosmic microwave background. The CMB appears slightly warmer in the direction we are heading and slightly cooler in the direction we are leaving behind, an effect known as the CMB dipole. This temperature difference is our most precise measurement of our velocity relative to the cosmic rest frame, the fundamental backdrop of the universe. It confirms we are moving at a staggering speed of over 1 million miles per hour. This should be the end of the story, a simple confirmation of our motion. But it is not. When cosmologists like David Spergel look at other all-sky maps, like those of distant galaxies or radio sources, they find a similar dipole pattern caused by this same motion. The problem is that the amplitude of these other dipoles does not perfectly match the one in the CMB. There is a tension, a discrepancy that suggests something is wrong with our simple picture. Either our measurements are being affected by unknown systematic effects, or there is an additional, unexplained component to our motion. This dipole anomaly is a direct challenge to the cosmological principle, the foundational idea that the universe is homogeneous and isotropic, meaning it looks the same in all directions on a large scale. If the universe has a preferred direction, a cosmic drift that cannot be fully explained, it hints that our local patch of space is not entirely typical. One radical explanation is that we reside inside a vast, primordial inhomogeneity, a giant void or a gradient in the density of matter that was imprinted on the cosmos before inflation even began. Such a structure would generate large-scale flows, pulling entire superclusters of galaxies in a specific direction. These flows would add an extra velocity component to our local motion, one that would show up in some surveys but not others, creating the very mismatch we observe. To understand this, scientists use immense surveys like Gaia, which maps the positions and motions of billions of stars, to trace the gravitational tug of these large-scale flows. They also study the kinetic Sunyaev-Zeldovich effect, where the CMB light is subtly shifted as it passes through moving clusters of galaxies, providing another independent measure of cosmic bulk flows. The theoretical explanations reach back to the universe's first instance. Could superhorizon perturbations, fluctuations that were stretched far beyond our observable universe during inflation, be exerting a gravitational influence on our entire local volume? Perhaps long wavelength modes from the inflationary field itself set up a primordial gradient, a tilt in the fabric of reality that our galaxy is still sliding down. This idea elegantly links several puzzles, as such a gradient could also influence the local expansion rate, potentially offering a new angle on the persistent Hubble tension. The implications are profound. If future data from next-generation observatories confirms a fundamental mismatch between the CMB dipole and other cosmic dipoles, it would mean that the universe's isotropy is an illusion painted over a more complex, textured reality. Our motion would not just be a relic of local gravitational pulls, but a fossil of pre-inflationary asymmetries, a memory of conditions that were mostly overwritten by the universe's violent expansion, but not completely erased. What does our trajectory through the void ultimately reveal about the vacuum of space itself, and its potential for a far more dramatic transformation? Our universe may be living on borrowed time. The vacuum of space, the very fabric of reality, might not be in its true, lowest energy state. Instead, it could be a false vacuum, a state of precarious, temporary stability, like a ball resting in a shallow dip on the side of a much deeper valley. A single, random quantum event could be enough to nudge it over the edge. This is the theory of vacuum decay, a process that would rewrite the laws of physics and erase the cosmic history we have been tracing. If this decay were to begin somewhere in the cosmos, it would create a bubble of true vacuum. The walls of this bubble would expand outward at nearly the speed of light, a wave of fundamental transformation. Inside this bubble, the laws of physics as we know them would cease to exist. The forces that hold atoms together would change, and all structures, from galaxies to individual particles, would be instantly dismantled. It would be the ultimate eraser, a final overwrite of the Cosmic Palimpsest. Yet, this terrifying possibility also offers a way to see deeper into the past. Just as the decay could happen in our future, it might have already occurred in our distant past. Our entire observable universe could be inside one of these true vacuum bubbles, a safe harbor that nucleated long ago within a vast, inflating false vacuum. The work of physicists like Sidney Coleman helped us understand the quantum mechanics of this tunneling process. He showed how this transition could create bubbles of a new reality, their birth a violent event that would leave its own distinct scars. If our universe did form this way, then the moment our bubble nucleated and began to expand would have been a cataclysm. The collision of our bubble wall with the surrounding false vacuum, or with other bubbles, would have released an immense amount of energy, sending powerful ripples through the infant cosmos. These ripples would have imprinted themselves onto the cosmic microwave background. Researchers like Hiranya Paris have searched for these signatures, scanning the CMB map for specific patterns. The most telling sign would be concentric rings of temperature variations, the ghostly echoes of long-ago bubble collisions. These circular bruises on the sky would be evidence that our cosmic history was indeed overwritten by a phase transition, a shift from one vacuum state to another. This idea is deeply intertwined with eternal inflation. The false vacuum background, with its repulsive energy, drives a relentless, exponential expansion. Within this churning sea, bubbles of true vacuum like our own spontaneously form. The energy released when these bubbles collide would generate a unique background of gravitational waves, a specific hum that future observatories like LISA could potentially detect. The very field that gives particles their mass, the Higgs field, is central to this story. Measurements at the Large Hadron Collider suggest that the Higgs vacuum might indeed be metastable. This means the vacuum of our universe is not perfectly stable, but resides in that shallow dip, potentially capable of decaying. The mysterious dark energy accelerating the universe's expansion could also be connected, perhaps influencing the rate or likelihood of this decay. How could the threat of total annihilation illuminate forgotten stories? Because if we found evidence of a past decay event, it would reveal a transient phase in the universe's evolution, a chapter that was mostly erased when our bubble formed. The specific properties of the rings in the CMB, or the spectrum of the gravitational wave background, would tell us about the energy difference between the false and true vacuum. This would be a direct measurement of a reality that existed before our own, a fundamental layer of the palimpsest that was overwritten at the birth of our cosmos. The search for these signatures is a hunt for the ultimate cosmic context, a way to understand not just the story written within our universe, but the story of how our universe itself came to be. Our journey across the layers of the cosmic palimpsest brings us to a profound realization. The universe is not a static monument, but a dynamic, breathing archive. Its history is not lost, but layered, written over and over again in the faint whispers of the cosmic microwave background, the silent architecture of dark matter, and the echoing crashes of black holes. Each method of inquiry, from reading the primordial recipe of light elements to mapping the vast voids between galaxies, reveals the same essential truth. Our cosmos actively preserves its past, even as new, violent events constantly overwrite it. The anomalies we uncover are not failures in our understanding, but guideposts. The Hubble Tension and the stubborn Lithium Problem are not mere puzzles to be solved. They are whispers of deeper, untold narratives, hints of physics from a time before time or perhaps from realms beyond our own. Every observation we make, from the coldest spot on the sky to the faintest gravitational chirp, is a step toward decoding these lost chapters. This is not the end of the story, but an invitation. Let this exploration be a call to your own curiosity. Which of these cosmic mysteries resonates most deeply with you? Share your thoughts in the comments below. Join the conversation and subscribe to continue delving into the greatest enigmas of space. The great cosmic palimpsest awaits further reading, and its next secret could be uncovered with your